a logistic model. The equation is a bear. Don't focus on the equation right now. I'm going to have a video to go with the equation if you want to watch it. I'll record it on Friday at some point. But the logistic model, I personally think, should be paired up with the exponential, because the exponential assumes that the growth will continue unchecked, unabated forever. Well, that's great, except a lot of things that grow exponentially run out of resources, i.e. a virus in your body or a cancer cell. One of the reasons cancer is so awful is because it multiplies so quickly. It's got a rate of reproduction. Let's make it simple. Let's say it doubles every, what do you think?
12 years.
12 years? It's quicker than that. Let's say it doubles every 2 months. So 1 becomes 2, 2 becomes 4, 4 becomes 8, 8 becomes 16. And that's terrifyingly fast. Well, the problem is, it can't do that forever. Eventually, unless it's caught and knocked down, it kills its host. Which means that eventually it runs out of resources to continue doubling. It's still going to keep trying. It's still going to keep trying, but maybe it can't get from 8 to 16, it'll maybe from 8 to 14. And then those 14 try to double and make 28, but they can't make 28, they only make 25. And those 25 are going to try to make 50, so it's almost like it's constantly getting it knocked down. It's still growing, but the rate of growth slows as time passes. So that's why I like looking at logistic as well as exponential. Logistic is if you, I call it this, tempered exponential growth. Tempered or suppressed exponential growth. And the data, the key element of the data, and again, this is if you see it again, and some of you business folks might see it again. The key element of the data is it looks like exponential, and then it makes a turn, and it looks like upside down exponential. It can also go the other way, but this is a pretty common representation of it. And then it does that. And it's got, as Randall said, it's got asymptotes. Okay, the exponential had 1. It had an asymptote across the x-axis. Well, logistic has 1 too. But it also has a ceiling asymptote. A ceiling being a number that it can't go above. Exponentials grow forever, but a logistic can't. It's got a constraint on the top. The UN, the United Nations, has used this model to predict how many people the carrying capacity of the world is at. I think I have a quiz for you guys to look at this one, I think. I don't know if I posted it for this week or not, I may have. If I didn't, I'll post it for you soon. Because, you think about it, the human race doubles every 40 years. What was I talking to this about on Wednesday? Carrie, talking to you about it. The human race, if you look at history, the human race doubles every 40 years. Okay? Go back in time, it was roughly 6 billion in the year 2000. It was roughly 3 billion in the year 1960. It was roughly 1.5 billion or whatever it was in the year 1920. It almost exactly doubles. Well, we can't just keep doing that, now can we? Well, we could try. We're pretty damn good at trying. But eventually, what's going to happen? Well, we're going to die. We can still reproduce before we die. But why can't we just keep doubling without bound? Resources, habitat, food, fuel, whatever. I mean, there's all kinds of resource limitations that we have. So we might be able to go from 6 billion to 12 billion. But going from 12 to 24 billion or 24 to 48 billion is a different story. Now, I've often been told that there's enough land on Earth that you can put every single person on Earth in Texas. No, in the Grand Canyon is my favorite. You can put every single person on Earth in the Grand Canyon with roughly about a 10 by 10 office space to themselves. That's fine. Do you want to, that's, mathematically you can figure that out. You can figure out the volume of the Grand Canyon. It actually works. It's pretty crazy, actually. The Grand Canyon's, who's seen it? Grand Canyon? Yes, it is way bigger than you think it is. It is one of the, I used to ask Math 105 students this question on the first day of class. How many jars of peanut butter would fit in the Grand Canyon? I stopped asking it because people didn't like it very much. I think it's a fantastic question. Well, the best answer I ever heard was, what size jar? Ha! You get an A. Ha! You get an A. But the idea is you can cram every single living person in the Grand Canyon, but that's not life. That's cramming. That's sardines, right? And just because we've got all this space doesn't mean that every spare square foot of it is habitable. I mean, you'd have to put some of those 48 billion at the North Pole, or Antarctica, which I'm sure the real estate values are very low down there, for obvious reasons, like temperatures. So the idea is this is a pretty good model for population growth. Because yeah, when a species is thriving, it tends to exponentially grow. but then as resources are consumed, it tends to do this. What's interesting is when you apply this over time cycles, when you look at like how deer and elk populations coexist with, say, wolf populations, there's a cool little dance that it does, whereas one population goes up, the other one follows it, and then when this one gets too high, this one's super stoked, and then this one dies off, and this one takes a little bit longer to die off, and it's kind of like a parallel. For those of you taking more biology classes or more mathematics classes might see that predator-prey model. It's a very useful model for a lot of ways, mostly because of that idea of there's a ceiling on what you can do. I've used it for people in their PhD theses when they're trying to see if there is some indicator for success or failure. The most recent one I looked at was a student was trying to figure out, he had like 30 different economic indicators for small businesses. Some had failed and some had made it. And he was trying to see which indicators, if any, would be a predictor for if a business is going to make it or not. And some of these were as far-fetched as, you know, the color of the walls inside. If you could code the colors of the walls, bright or not bright. And what's interesting is, you can see how that would actually work. Here's the business fails, here's the business does well, and the equation gravitates towards one of those two. That's the idea. You get that data and you plot it on one of these curves. It's a wonderful little model. Have you ever heard of a logistic forecasting model? That's what you're looking at here. So you might see it again. You might never see it again. In which case, I put a quiz up about world population. You might or might not do it. You might never see it again after that. That's totally fine. But just realize exponential growth, which we're going to spend the next 5 days or 4.5 days kind of playing with in the world probability, does have a cap in certain instances. Populations, resource models, ceilings, and things like that. And there's our model. Look at that friggin' gorgeous 2 boards. Modeling, yay! That's what I'm saying. That's what I'm saying. Let's take 5. We'll get back to more data collection because I want to collect some more data with you guys. Let's figure out what's over that, Matt, too. I want to find out what's going on with that back there.
How much plastic?